Okay, so today is kind of a, when you think about not a totally DSP lecture, although I've got motivating with DSP concepts. In a way, it's kind of an introduction to the kinds of algorithms that you would start to look at in a course like a numerical optimization or a computational optimization course, right? How do you actually achieve minima of multidimensional functions? And so just to remember from last time, what we talked about was the Wiener filter. I guess last time doesn't have a hyphen in it, but it's too late. And the way that worked was we had a desired output, d of n, which, as we discussed in the context of the Wiener filter, was usually some future or maybe previous value of the signal. And then we had an input process, x of n, and we wanted to compute the kind of optimal filter h of n to minimize a cost function. And we called that cost function j, and we said that was basically the expected value of the square of the error, where the error was defined as the difference between what I want, the desired output, and the result of filtering the signal with a given filter. Okay. And we showed that we could analytically, that is explicitly, figure out what was the minimum by solving what were called the Wiener-Hopf equations. Okay. So this is all still review. The optimal h is given by solving the Wiener-Hopf equations. And basically that meant that we had a big matrix R, that was the autocorrelation matrix. And that has this kind of special structure. So we called that R. And then we had a vector of the unknown filter taps, H0 through Hm minus 1. And then we set that equal to this right-hand side vector, which we called P. Where this P was basically defined as a correlation or a covariance between the n minus kth sample and the desired guy. Okay? And of course, when the desired signal is actually one of the original x's, then this right-hand side also turns into a bunch of correlations, autocorrelations, or R's. Okay? And so this is the way that we would set up the problem. And then in MATLAB, you would solve it, for example, by doing this, R backslash P, or R inverse P, right? Okay. And just to refresh your memory, we also showed what the optimal cost was for that best filter, right? We could figure out, if we solve this equation and plug it back into our expression for the error, we could find out that the cost for any candidate H was related to the R's and the P's like this, and that the best J, which I'm going to call J tilde, this was like the best we could do. Okay. And so all that is good. And let me just say a few words today about how this process might actually work in practice, right? So in practice, we don't exactly know the autocorrelation matrix or this P vector, right? And the reason we don't know it is that the autocorrelation and the P, are kind of coming from these stochastic, somewhat unknown random signals, right? So in practice, what we do is we estimate the R and the P from the data that we're getting, and then we use them to plug in to get the best filter, okay? And so in practice, R and P are estimated from data, and thus are functions of n. Right? What I mean by that is that, at current time n, I have all the input signals that I've ever seen, and I use all that input information to build up a good estimate of what that autocorrelation should be, right? So in practice, what I might say is that, I might take the last set of values of x, right? So this is like saying, tell me the last, the current value of x and the previous m minus 1 values of x. So this is a length m vector. And what I can do is say, okay, so here's the most recent set of my input, okay? And here is my set of kind of candidate filter taps. So I might have, this is my estimate of the filter at time n. And then what I get is an estimate of the desired signal, d hat, at time n, which is basically gotten by filtering the signal like this, right? This is like saying, what would my estimate of the desired signal be at time n using the previous values of the signal that I have here? And a very compact way to write this is basically saying I take the filter coefficients and I dot product them with this vector u, right? So that's like I take the pairwise multiplications and I add them up. That's really the same thing as filtering the signal. Okay. And then my error is the desired signal minus my estimated signal. So all I'm really doing here is writing things in slightly different ways, right? And so here what you can see is that in this sense, the filter is going to be adaptive in that we are kind of constantly updating this h of n, my best estimate of what the filter should be, at every point in time, given the information that I've accumulated so far. Okay? And so the idea is that, as in theory, as more data becomes available, I get better estimates of the autocorrelation matrix, and my h converges to the best possible h. Okay? So let me just kind of write that down. So the filter is adaptive in that h of n converges to some h that hopefully is good close to the optimal h as we see more data. Right? And kind of one way I think about this is that, like what we talked about in probability, right? If I wanted to estimate the sample mean or the mean or the covariance of a random number, and all I was seeing was realizations of that, right? So the more realizations I see, the more the sample average of my numbers should get to the mean, right? We proved some things in probability, things like the central limit theorem and the law of large numbers and stuff like that, that told us that the more data we see, the closer our estimates are to the truth, right? And that's kind of the same thing that's happening here. In theory, the more input that we see, the better of an estimate of the autocorrelation matrix we should get, and the better our estimate of H should be. Okay? So, you know, the Wiener-Hopf equations tell us explicitly, if I give you all of this past data, it tells me how should I estimate the, it tells me how should I estimate the H's, right? The problem is that if I'm getting a lot of data at high rates, for example, it may be impractical for me to kind of keep on updating my estimate of H by solving the Wiener-Hopf equations all the time, right? And so instead, we may want a more computationally nice way of pushing the estimated filter taps towards the ones we want without explicitly solving these equations, okay? And that's just a fancy way of talking about numerical minimization algorithms, right? So this is something that maybe, I'm not sure which class you would have seen optimization algorithms in. So this is kind of like a maybe introduction to those kinds of algorithms, right? Where sometimes you have a cost function that so here basically what we have is we have a cost function related to the H, right? And in our case, with this particular problem, we're lucky that we know exactly how to optimize this cost function. I can write this equation and know what the optimal answer is. But there are some cases where it's not so easy to explicitly write what the optimal thing should be, right? In that case, you're forced to deal with what are called numerical or iterative optimization techniques, where you kind of try and recursively or iteratively find your way to the right answer, right? And that's the way that in practice most minimization works, because in theory, in classes we try and give you problems where this function is nice and you can take the derivative set equal to 0 and solve for H. But in the real world, cost functions are usually not so nice, and you're faced with having to solve them in a more numerical way, okay? And so kind of the idea is that what I'm going to talk about today is a very simple algorithm called steepest descent, or sometimes called gradient descent. And this is usually the first choice for trying to minimize some cost function that you don't know explicitly how to solve, okay? And so the idea is that we will, we have a cost function j, and so I'm trying to think about the best way to sketch this for you. So what was the definition of the gradient in kind of the vector calculus world, right? And this is where my drawing is going to kind of suck. But the idea is, suppose I have some sort of a cost function like this kind of upside down bowl, okay? And I want to interpret what the gradient means at a certain point, right? So it's kind of like a function of x and y, right? So in calculus, like third semester calculus, you talked about the directional derivative of a function. That basically meant if I had a function of x and y, I have the option of taking a vector u, right? So if I say, okay, I can take the derivative in this direction or that direction or this direction or whatever, right? And kind of what I'm doing is saying, how rapidly does the function increase or decrease in that direction? And the definition, in some sense, of the gradient is the direction where the decrease of that function is the steepest, right? The gradient points in the direction where things get smaller the fastest, right? So the gradient of an ND function points in the direction of, I guess I would say the most rapid change is the best way to think of it. Okay? And so, for example, if I was trying to, I guess I drew this like an upside down bowl. If I drew it like an actual bowl, kind of what I want to do is I want to imagine that I want to arrive at the minimum, right? So actually maybe I should just draw this slightly differently. So if I drew this as an actual bowl, right? So the idea is that here, I want to arrive at the minimum, the bottom of this bowl, right? And I may currently be at some other point on the bowl, right? So how do I find my way to the bottom of the bowl? What I should do is I should move in the direction where the bowl is descending most steeply, right? That will get me to the bottom of the bowl the fastest. If I take a step along like the side of the bowl where things are not changing that much, I'm not going to arrive at where the minimum is, right? So that's the name of the game, is at every step I want to take a step along the gradient, right? And so the idea here is that the filter at time n plus 1 is the filter at time n. And what I'm going to do is, since I want to decrease the cost function down to 0, what I'm going to do is I'm going to take a step along the gradient of the cost function. So basically this is the gradient. And this number here, this mu, is what we call a step size, right? That controls how much of a step I take along the gradient, right? I mean, any step that I take in the direction of the gradient will reduce my cost function locally, right? So if I take very small steps, I will definitely be kind of chewing away at the cost function, making it less and less, right? If I take huge steps, it's possible that I may kind of overshoot my minimum because, unfortunately, real-world cost functions have, you know, I don't want to explain this. Right, so if I think about the cross-section of this bowl, kind of the idea is that imagine that these are like contours of the bowl seen from above, right? So if this is xy down here, and this is xy down here, the minimum may be right in the middle. That's where I want to get to, right? And the gradient at a given point like this points in the direction of fastest decrease, right? So if I take small steps along the gradient, you can see that eventually I'm going to kind of get towards the middle of the bowl. If I took a huge step along the gradient, right, I might just fly right past the minimum. And then over here, I would kind of seesaw back and forth and take another big step, right? So the tuning of how big of a step I take along the gradient in every iteration is really important when it comes to figuring out whether an algorithm like this will actually work, okay? And so that's what I want to talk about a little bit today. So let's just pause and ask big picture questions. Yeah?
So is it possible if you were stuck in a local minimum instead of like a minimum?
Yes. So it's definitely possible that you get stuck in a local minimum of the cost function. And that's actually a very difficult problem in numerical optimization in general, is how to find the overall global minimum of a cost function, right? So if I have a cost function that looks like, looks from the side like this, right? So I can easily have a situation where I take steps along the gradient and then I end up at a point where the gradient is 0 here and I stop, right? I will never find this deeper global minimum, right? And that's just a problem for numerical optimization in general, right? You obviously, in the real world, you would love to have cost functions that only have one local minimum, but that's not always true. And so this is a little bit beyond the scope of this class, but things you could do, for example, would be to start your minimization from lots of different points and see, you know, all the points over here are probably going to converge to this guy, and all the points over here are probably going to converge to that guy, and then you choose the one that gives you the lowest thing at the end of the day, for example. There's really not any satisfying answer to find the global minimum of a function that has lots of local minimum. And that's a problem that kind of in my work we have to deal with all the time. And so one thing I'm not going to talk about too much is the value of finding a really good guess for where the minimum should be, right? So if I was to guess that the minimum is around here, right, any of my choices would get me to the right minimum. But if I guessed wrong and said maybe I'm over here, then I might end up at a local minimum. So there's kind of two aspects. One is step size, and one is a good initial choice of where to start. Yeah. Okay. So let's think about the specific Wiener filter that we talked about last time and make it kind of a little more concrete. So our cost function for the Wiener filter at time n would basically be like saying I take this sigma, I take the filter I have at time n, and I take this guy here. And so what I would do is I would take the derivative of this or I'm sorry, the gradient of this, right? Remember that the gradient is what we do when we have a function of many variables, right? If there's only one variable, it's the derivative. If we have lots of variables, then I have basically one entry in the gradient for however long this is. So this is really like an m by 1 vector. And taking the derivative basically gives us negative 2p plus 2rhm, right? This is constant, so that goes away. And this here, I'm skipping the details a little bit. For example, why is the derivative of this equal to 2p? Well, you know, I can think about going back to my scalar equation and saying, well, so, you know, what is the derivative of gradient of A transpose x, right? That's like saying I take the derivative with respect to xi of a1 x1 plus am xm, and that's just going to pick off whichever one of these guys multiplies with this, and so this gives me that this is true. That's why I get this. It's a little more complicated to show why the gradient of this quadratic form gives me this, but if you multiply it out element by element, you can convince yourself why it's true. So this is kind of like a vector version of taking derivatives. And so, again, this is an m by 1 vector, right? This is an m by m matrix times an m by 1 vector, so that's also an m by 1 vector. And so now what the steepest descent algorithm would be telling me when we say I get my next filter by taking the filter I have now, and let's refer back to my thing, I'm going to be taking minus 1/2 mu times this gradient, so these 2's and these negatives are going to cancel out, and what I'm going to do is take a step along this vector direction, okay? And so this is the steepest descent iteration that I would use. And you can see that if, you know, if this direction is equal to 0, that means that I have this, and this is actually just saying that the Wiener-Hoff equation is satisfied. Right? So if I'm already at the minimum, this thing in the parentheses is 0, and I don't move at all. Right? So once I've hit the minimum, then I stay there. Right? If I haven't hit the minimum, I keep on taking steps in such a way that will decrease my cost function more and more. Okay. And so kind of the key question is, how do I know that this system will, how do I know that this approach will work? Okay? I mean, I kind of sketched for you a picture of why I thought it should work, but really, if we're doing this seriously, we have to actually prove why things converge. Okay? And so I don't want to get into that too much, just because I wanted to save some time to talk about the exam. I have pages of notes about it, but I'm not going to belabor you with the point. Basically, the idea is that what we want is we want the error which is defined as the difference between the filter that I have now and the kind of ideal filter. We want that to get smaller and smaller, right? That means that we're converging to the right answer. And it turns out that convergence is related to the step size. Okay. So it seems kind of intuitive that if I take small steps, you know, not much can go wrong, but it may take me a long time to get to the answer. But if I take really big steps, it's possible that I may overshoot the answer and have to zigzag around. I may never actually get there. And so there's a nice proof that says that we need to look at the eigenvalues of the matrix R. Right? So R is this autocorrelation matrix that plays a role in all this Wiener-Hopf stuff. And so the idea is that if I have m eigenvalues of the matrix, then the proof, or the theorem, is that the error goes to 0 if this equation is satisfied for all lambda k. Right? It's kind of like saying there has to be a relationship between the eigenvalues of the autocorrelation matrix and the step size that I take. And this is going to be satisfied if, so this will be true if the step size is some positive number that is less than this relationship involving the largest eigenvalue of R. So again, I'm not going to prove why this is true, and I know that all of you are kind of fuzzy maybe on linear algebra anyway, but this is a good thing to, I mean, there's no reason why you couldn't understand this proof, and I believe it's in the Proakis book to take a look at it, but let's just assume that this is true. Kind of what this means is that as long as I have a step size that is not too large, my steepest descent algorithm will converge, okay? And so you still have to deal with kind of typical convergence problems, right? So I was drawing this picture before where if this is kind of like the overhead view of my cost function, you know, the step size being too small kind of has the result that I take these kind of little, slow, pokey steps, and I eventually get to the minimum, right? That means that I will get there, but it may take me like way too long, right? And of course, that in the real world, we're interested in algorithms that converge pretty fast, right? So in some sense, what I want to do is I want to crank up the step size as large as possible to take big steps along the gradient. On the other hand, if I take step sizes that are too big, kind of what may happen is that, you know, here, the gradient is pointed this way, right? And if I take a big step, maybe I go over here, and if I take another big step, maybe I go over here. So maybe I eventually get to the minimum, but I kind of zigzag my way there, right? So this is like step size too big. And actually, you know, if you remember the lingo from signals and systems, right, this is kind of like the equivalent of overdamped and underdamped, right? So when you have something that kind of oscillates wildly, right, that's kind of like an underdamped system. And so, you know, ideally what you want is a set of bold, confident steps that will kind of take you right to the minimum without bouncing around a lot. Yeah.
So can we have like a change in size of step size?
Yes, so that's another good question. So you can, and actually the way I kind of drew it here, yes, so the question is, can you change the step size? And the best optimization algorithms do adaptively change the step size as you go forward, right? And so there's a well-known algorithm in my community called the Levenberg-Marquardt algorithm, right? Which is kind of like, I mean, it's not exactly gradient descent, but it's related to things like the gradient of the function. And in that case, a big part of that algorithm is adapting the step size as you go, right? Yes, so the steepest descent algorithm is basically the dumbest numerical optimization algorithm that you could make, right? But it will work slowly, perhaps, if you choose your step size small enough. But there are better algorithms that adapt the step size, right? And we'll talk about that a little bit, actually, as I go forward here a little bit. Okay, so just questions on the big picture. So I mean, you can apply this. I mean, I talked about it in the context of the Wiener filter, but you can apply it to basically any cost function that is some, as long as you can write down what the gradient is, then you can apply steepest descent. And even if you can't write it down explicitly, you can always estimate the gradient by kind of, if I want to estimate the gradient of a function, what I can do is estimate the derivative by looking at the value here and looking at the value nearby and taking the difference and dividing by the length of my vector. And that's how we defined the derivative way back when in Calculus 1, right? Is basically you look at the difference between a little bit of a step away, where I am now, and you divide by the length of the step. You can approximate the gradient in that way, even if you don't have the actual numerical answer for it. Okay, so all this machinery, question? Well, it's used all the time. I mean, many times. So I can't even think of a good example. So basically, the idea is that there are so many situations where you have a function of some unknown parameters, and you've defined a cost for how good a set of parameters is, right? And you want to minimize that cost function to find the best set of parameters, right? That happens constantly in real-world systems, right? In a way, right, you can think about what you're doing now on the homework as an example of that, where the parameters are the unknown coefficients of the AR process and the unknown variance of the noise, and you see some data, and now you want to fit the data to the parameters as well as you can, right? So there's an example where you have a whole bunch of unknown parameters, you've got some data in front of you, and you want to drive the cost function to be as small as it can be, right? Or you imagine that you're trying to, you're doing this problem with, pressure waves and acoustics, right? So I mean, there must be some parameters of the system that you don't know that you would have to estimate from the data, right? How would you estimate them? You'd collect a bunch of data, and you would try to make your observations fit as much as possible with the unknown parameters, right? And so there are, basically almost every real world scenario corresponds to parameters and a cost function that you want to minimize, right? That's the way of the world in the kind of work that I do all the time. Right? Does that make sense? Yeah. Okay. Question? Yeah. How can you determine the cost function? So in this case, the cost function in my world, right, was defined by the cost function corresponding to the Wiener filter, right? So this told me that if I gave you a candidate for H, this would tell me how good that candidate is, right? And I want to make this thing on the right-hand side as small as possible, right? So here, this cost function came out of trying to minimize the error between the desired thing and the observed filter response, right? So the way I set up the problem generated for me my given cost function, right? But in the real world, that cost function, comes from, it's very problem specific, right? So what I set up here was the specific cost function for finding the best filter to match the desired output to the actual output, right? And the Wiener filter is defined as finding that optimal. So the Wiener filter defines that cost function for that problem, right? But there are many different cost functions for many different problems, right? Does that kind of make sense? I mean, the cost function in some sense is given to you by God, right? You decide, what do I care about? What do I want to minimize, right? So again, we can think about the cost function. So let's think about filter design, right? So there's another case where there's a cost function, right? So the cost function in that case, we talked about several of them. So if we're designing an FIR filter, what one cost function I talked about was trying to minimize the difference between the designed filter's amplitude response at a whole bunch of sampled points and the actual, and the desired response, right? So there we have a big sum of squares problem that says how different is my actual design filter from my ideal filter. And we showed that you could solve that with a linear least squares problem that's actually not that different from the Wiener-Hoff problem, right? It also is like a big matrix equation, right? And so you could imagine that you could adaptively adjust your filter taps in the same way as I do this. Instead of trying to solve the backslash operator in MATLAB like you did in that homework, you could apply this steepest descent algorithm to find the best filter taps numerically, right? And a different cost function, right, would be the Chebyshev cost function, right? So there, I have a very different cost function that says I want to minimize the maximum ripple or deviation from the amplitude response, right? So that is a much different cost function than something like this. And that's even harder to write as a function that I can take the derivative easily of. But the point is I can write what that cost function is, right? And so I, as the user, am making a choice about what do I consider to be the measure of goodness of my set of parameters, right? And the Chebyshev is a different set of considerations, a different decision than a least squares thing, right? So there is no right answer. It's what I have chosen as the user as what's important to me at the time. Right? Okay. So, other questions or comments? So, one thing that is a little bit tricky in this case is that in order to define this iteration, right, I have to know this P and this R, right? And the problem is that those things are generally not given to me on a plate, right? I mean, I have to estimate them from the data. And so kind of a different way of saying that is that the steepest descent algorithm is deterministic. For example, in this case, it assumes that R and P, which are the key parameters that define the cost function, are entirely known to me, right? Whereas in practice, I don't really exactly know what those are. I have to estimate those from the data also, right? And so there's an algorithm called the LMS algorithm, which stands for least mean square. And that's what's called a stochastic gradient algorithm. What that means is that not everything is known, but parameters, key quantities are estimated from the data that I have, which is going to be noisy, right? So kind of the idea is that what I would do instead would be to say, okay, you know, I don't know R exactly, but we can estimate R as R hat n un transpose. So what do I mean by that? So remember what I defined this un as, right? The un was defined as xn minus 1 all the way down to xn minus m minus 1, right? Just the vector of the most recent m value of the signal. So what does un transpose look like? Well, it's going to look like, over here I'm going to get x of n times x of n. Over here I'm going to get x of n times x of n minus 1. Over here I'm going to get x of n times x of n minus m minus 1. Here I'm going to get x of n times x of n minus 1. Here I'm going to get x of n minus 1 times x of n minus 1, and so on, right? So this is a matrix that is made up entirely of data samples. Question?
So you're assuming that all the vectors are column vectors unless there's a transpose?
Yes, I realized I should probably put a transpose there to make it really clear. So here un is a column vector.
I think you did that on a previous slide too.
Yeah.
But,
I generally always assume that vectors are column vectors, but I may have been a little sloppy with when I put this on before. Yeah. So the idea is that here, this is like a column vector, right? So this is like an m by 1 column vector times a 1 by m row vector. That gives me an m by m matrix. And that m by m matrix looks like this. And the idea is that if I was to take the expected value of that matrix right? So the expected value of this is R0, right? It tells me that those two elements have 0 lag between them. Here, the expected value of this is R1 because these two elements have a unit lag between them. The expected value of this is Rm minus 1 because those guys are separated by m minus 1. And similarly, the expected value of this, again, these guys are separated by 1, these guys are separated by 0, right? So in some sense, this kind of estimate of R is a probably pretty noisy estimate of the underlying covariance matrix. So for example, there's nothing that will make the diagonal elements of this R hat sub n the same, right? Even though I know for the ideal autocorrelation matrix, the diagonal looks like R0 is all the way down the line. Here, these are going to be like the sum of the squared value. These are going to be like x of n squared, x of n minus 1 squared, and so on. Those are all going to be different values, right? So this matrix is going to be kind of a hairy approximation to the true underlying autocorrelation matrix. But if I took the expected value of it, I would get what I wanted, right? And so the question is, can we still do this steepest descent algorithm by replacing the R that I had here with my kind of crappy approximation that I get from the data? And the answer is yes. So basically, the idea is replace R and P in the steepest descent algo with their kind of data-driven approximations. And it turns out the result of that is this. So what I get is h of n plus 1 equals h of n plus some step size, and then I define this un vector right. So this kind of turns out to be, so this un transpose is where the R hat comes from, right? So it's kind of like saying that my estimate of j at time n is approximately this turns into un hat, and this turns into un times the desired thing. So here, really the way to put this on would be to make these little hats, right? These are like saying, these are my estimates of the next filter. So now all of this process here, the U's are entirely driven from the data that I get at every point. So kind of what I'm doing is I'm taking these frames of m minus, or the last m points, I'm using it to make my U vector, and then I'm kind of using that to drive this filter evolution process. And so the problem is that now, because this step direction may be kind of crappy, I may not actually be taking steps exactly along the true gradient. So I may not be able to do as well as I did if I actually knew what the gradient should be. Instead, I'm taking a step that is probably a little bit off from the best thing. But as long as I'm taking steps that are like kind of in the right direction, I don't have to take a bold step right along the gradient to decrease the cost function. As long as I take a step kind of in the right direction, I'm going to get there eventually. And so, again, people have done a lot of analysis to figure out, well, how well does this convergence algorithm work, right? So let me just say, how well does this convergence algorithm work? So again, just some bullet points about that. Basically, we still have kind of the same requirement on the step size, The problem is that, we don't know how to compute the eigenvalues of the underlying R, right? So it turns out that, this is really hand-wavy, but maybe I'll just say this in a super slangy way. So if things go well, if we choose basically so this guy here is what's called the tap input power. So the idea is that here is an equation for the step size that will only depend on the values of the signal that I've seen, right? So basically what I'm looking at is the sum of the squares of the m previous entries. That's a number that I can compute from the data that's coming at me, right? And so that means that I can kind of adaptively change my mu based on the most recent sum of squares that I've gotten, right? And it turns out that this is kind of a approximation to the underlying actual lambda max that I don't know, right? So the nice thing is that this depends only on the data that I see.
So in this case, mu is a function of n.
Right. So in this case, that's right. So mu would kind of be a function of n, right? And in fact, you could do a little bit even better. Actually, that's okay. I mean, yes, I have some further details in my notes, but I think this is probably fair enough to say that basically, un kind of can change adaptively. Typically, maybe you want to have like a little constant underneath here that prevents the denominator from becoming 0 when all the inputs happen to be 0. So you kind of have a little bit of an extra thing here to make sure that you have no convergence problems, right? So that's kind of the big picture. I mean, this is very many miles up view of how numerical optimization can work in the real world. And if you're really interested in this kind of material, there are whole courses that talk about it. So for example, I think there's a numerical computing course next semester in the CS department. And oftentimes in the math or MATP departments, you'll see courses that are called things like, computational optimization, numerical analysis. Those are all kinds of courses that talk more about this kind of process, right? And so, just like for all the filter design stuff, MATLAB knows a lot about optimization. There's a whole optimization toolbox. And, if you look under the hood of MATLAB, you'll find that it knows all sorts of different algorithms, Steepest has said, and a lot of smarter ones than this. So if you're ever in the position of having to optimize a function of a whole bunch of parameters, all this kind of stuff is built in. But just in the same way that we're teaching you what's under the hood of MATLAB, the numerical computing course will teach you what's under the hood of the optimization toolbox. And I think those are really interesting courses because, it's kind of useful to understand what is the right algorithm I should choose for a given problem and how fast should I expect it to converge. Those are kind of, you can't just kind of throw a problem in MATLAB and expect it to solve it, all the time. You have to kind of know what's actually going on inside the algorithm. So this is just a hint of a suggestion of how those kinds of algorithms are applied to DSP. Okay. Any questions about this stuff? All right. So I will, I think now, stop this.